Hello everyone. Welcome to the lecture series on health management. We discussed a few important terminologies for network analysis in lecture number 30. In this session, we will discuss the steps in network analysis. The complete network analysis can be divided into 8 steps. Step 1. Analyze and break up the entire project into specific activities and events. Step 2. Determine the interdependence and sequence of those activities. Step 3. Draw a network diagram. Step 4. Analyze to estimate the completion time. Step 5. Identify the critical path from the network diagram. Step 6. Plot the timelines on a Gantt chart. Step 7. Calculate the probability of completion of the project. Step 8. Monitor the progress of the project and if required update the CPM or PERT diagram as the project progresses. Let us discuss each step in detail. Step 1. Analyze and break up the entire project into specific activities and events. Clearly define the project scope, objectives, and deliverables. As the project is a set of a large number of activities, we need to list those activities. A work breakdown structure breaks down projects into manageable sections. Start with the main project deliverables and break them down into subtasks. Determine key milestones that mark significant achievements in the project. These milestones provide a high-level view of progress and help in tracking the project's overall timeline. You can display your work breakdown structure either in the form of a tree structure or in the form of a list or table. These are the outlines of a tree structure and a table format to represent the work breakdown structure. Step 2. Determine the interdependence and sequence of those activities. All activities in the project are performed in a certain determined sequence. Some activities will depend on the completion of others. Listing the immediate predecessors of each activity will help you identify the correct order. Identify the start and finish activities and determine the logical order and dependencies among tasks. Also, identify activities that can be performed concurrently to optimize project timelines. To correctly identify activities and their precedence, ask yourself these 3 questions for each activity. What activity must be completed immediately before this activity can start? That means predecessor activity. What activities must follow this activity? That means successor activity. What activities must occur simultaneously with this activity? That means concurrent activity. Step 3. Draw a network diagram. Once you have identified the activities and their dependencies, you can draw the network diagram. The network diagram is a visual representation of the order of your activities based on dependencies. This diagram can be drawn by hand or you can use specialized software or tools or project management software like Microsoft Project and SmartDraw. There are 2 main types of network diagrams, the precedence diagramming method and the arrow diagramming method. The arrow diagramming method is a type of network diagram in which activities are represented by arrows, which are connected through nodes. The tail of the arrow represents the start of the activity and the head of the arrow represents the finish of the activity. The length of the arrow is often proportioned to the duration of the activity. In the precedence diagramming method, activities are represented by nodes, which are connected through arrows. These arrows show relationships between activities. This is an example of both types of network diagrams. The upper figure is the precedence diagramming method and the lower one is the arrow diagramming method. There are certain rules to be followed while drawing a network diagram. Each activity is represented by one and only one arrow in the network. Each activity must be identified by 2 distinct events and no 2 or more activities can have the same tail and head events. Try to avoid arrows which cross each other. Use straight arrows. Do not attempt to represent the duration of the activity by its arrow length. Use arrows from left to right. Avoid mixing 2 directions, vertical and standing arrows may be used if necessary. Use dummies freely in rough draft but the final network should not have any redundant dummies. The network has only one entry point called the start event and one point of emergence called the end event. Inserting dummy activity. The dummy activity is inserted in the network in the two situations. 1. To make activities with common starting and finishing points distinguishable. 2. To identify and maintain the proper precedence relationship between activities that are not connected by events. For example, in this figure, activity A and activity B have the same tail and head events, which is against a rule of drawing a network diagram. So, we need to insert a dummy activity. This dummy activity can be inserted at any place as mentioned in the figure. This is another example where task B and task C have the same start and finish nodes. And task D is an immediate predecessor for both tasks B and C. So, we need to insert the dummy activity between task C and task D to maintain the precedence relationship. Let us understand it in the detail with an example. In a hypothetical project, there are 5 activities, A to E. This table shows their precedence relationships. If we look at Figure 1, activity C is represented by 2 arrows, which is against the rule of making the network diagram. In Figure 2, activity E is not in the network diagram, which is also against the rule of making a network diagram. So, we need to insert a dummy activity between activity C and activity D to make the diagram perfect. Common errors in drawing networks. The 3 types of errors are most commonly observed in drawing network diagrams. Number 1, dangling. To disconnect an activity before the completion of all activities in a network diagram is known as dangling. As shown in this figure, activity 5 to 10, and activity 6 to 7 are not the last activities in the network. So the diagram is wrong and indicates the error of dangling. Number 2, looping or cycling. Looping error is also known as cycling error in a network diagram. Drawing an endless loop in a network is known as an error of looping as shown in this figure. Number 3, redundancy. Unnecessarily inserting the dummy activity in network logic is known as the error of redundancy as shown in this diagram. Adding duration to the network diagram. Duration is added to the network diagram for each activity. It is usually mentioned below the arrow denoting each activity. For example, this table shows the precedence relationship and duration for activities. In the network diagram figure, the duration for each activity is mentioned below the arrow of that particular activity. Step 4 and 5, analyze to estimate the completion time and identify the critical path from the network diagram. We need to estimate the completion time for each activity. These estimates may be deterministic estimates or probabilistic estimates. Deterministic estimates are commonly used for those projects which are repetitive and where one has prior experience of handling similar projects. Probabilistic estimates are generally used for those projects where the time required to complete various activities is not known as a priori. If we are using deterministic estimates, then the method is called critical path method or CPM, and if we use probabilistic estimates, then the method is called program evaluation and review technique or PERT. To understand those estimates, let us discuss the CPM and PERT in detail. Critical path method or CPM. CPM determines the total calendar time required for the project. As it is based on the deterministic time estimates, it is based on a single time estimate of the average time required to execute the activity. This single time estimate is completely based on the prior experience of the project manager. The project's duration is fixed by the time taken to complete the path through the network with the greatest total duration. It is determined by adding the times for the activities in each sequence. This path is known as the critical path and activities on it are known as critical activities. If activities outside the critical path speed up or slow down, within limits, the total project time does not change. The amount of time that a non-critical activity can be delayed without delaying the project is called float or slack time. Let us understand this with an example. In this figure, the table shows the precedence relationship and duration for activities. A network diagram has been prepared for the same. In this network diagram, there may be 2 paths to complete the project, path 1, through activities A, B and E, and Path 2, through A, C, D, E. The total duration for Path 1 is 27 days after adding the duration for each activity in this path, which is 14 days, 3 days, and 10 days. Similarly, the total duration for Path 2 is 35 days after adding the duration for each activity in this path, which is 14 days, 7 days, 4 days, and 10 days. So, Path 2 is the longest duration of the path and is the critical path for this project, and activities A, C, D, and E are critical activities. Activity B is a non-critical activity. The difference between 35 and 27 days, which is 8 days, is the slack time. This means if activity B is delayed for up to 8 days, it will not affect the overall project completion time. Program Evaluation and Review Techniques, or PERT. PERT also determines the total calendar time required for the project. As it is based on probabilistic time estimates, there is always a great deal of uncertainty associated with the activity durations of any project. Therefore, instead of a single time estimate, we need to calculate the expected time for each activity from the following types of time estimates. The optimistic time estimate, or TO. It is the shortest possible time to complete an activity in ideal conditions. In this time estimate, no provisions are made for delays or setbacks. The most likely time, or TM, it assumes that things go in the normal way with few setbacks. The pessimistic time, or TP, it is the maximum possible time if everything goes wrong and abnormal situations prevail. However, major catastrophes such as earthquakes are not taken into account. The expected time, or TE, for each activity can be approximated using the weighted average of these three time estimates using this formula. Then, similar to CPM, the duration of the project is fixed by the time taken to complete the path through the network with the greatest total duration. It is determined by adding the estimated times for the activities in each sequence. This way the critical path is identified. Let us understand it with an example. In this figure, the table shows different time estimates for different activities in a project. The network diagram is drawn and all the time estimates for each activity are put on the top of the arrow for the respective activity. Then we calculated the expected time for each activity using the given formula and placed the expected time for each activity on the top of the arrow for the respective activity. Then finally determine the critical path just like the critical path method after adding expected times for different possible paths. Step 6. Plot the timelines on a Gantt chart. After identification of the critical path, we need to construct the Gantt chart with all the project timelines. Before constructing the Gantt chart, it is essential to understand a few terminologies. Earliest start time, or ES. It is the earliest time at which the activity can start given that its precedent activities must be completed first. Earliest finish time, or EF. This is equal to the earliest start time for the activity plus the time required to complete the activity. This means EF is equal to ES plus the time required to complete the activity. Latest finish time, or LF. It is the latest time in which the activity can be completed without delaying the project. Latest start time, or LS, it is equal to the latest finish time minus the time required to complete the activity. This means LS is equal to LF minus the time required to complete the activity. The slack time is equal to LF minus EF is equal to LS minus ES. This figure is a bullet diagram for each activity showing different times and is an example showing the way to represent the different times for each activity in a network diagram. Following are the steps for constructing the Gantt chart. 1. Schedule critical tasks first. Critical tasks are those tasks for which there will be no slack time. That means the earliest start time will be equal to the latest start time, or the earliest finish time will be equal to the latest finish time. 2. Place time windows for non-critical tasks. The time window for non-critical tasks is calculated by deducing the earliest start time from the latest finish time. This is slack time plus the duration of the total activity. These are windows in which the activities can float. That's why the slack time is also called the float time. 3. Schedule the non-critical tasks according to their earliest starting times in the time windows. 4. Indicate precedence relationships. This can be represented by dashed lines connecting the endpoints and starting points of different activities. Step 7. Calculate the probability of completion of the project. Let us understand this with an example. In this figure, the table shows different time estimates for different activities in a project. The network diagram is drawn and all the time estimates for each activity are put on the top of the arrow for the respective activity. Then we calculated the expected time for each activity using the given formula and placed the expected time for each activity on the top of the arrow for the respective activity. Then determined the critical path by adding the expected times for different possible paths. The total duration for the critical path is 36 days after adding the expected times for each activity in the critical path. The next hypothetical question is, what is the probability that the project would be completed in 41 days? The probability of meeting a specified completion date is calculated by this formula. Z is equal to the due date minus the expected date of completion divided by the standard deviation of the critical path. First, we need to calculate the standard deviation for each critical activity. The SD of the time is calculated with this formula. We have calculated SD for each activity. Then, we will calculate the variance for each critical activity. The variance is the square of SD. Now we will calculate the total variance for the critical path by adding variances of all the critical activities. Then we will calculate the SD of the critical path by doing the square root of the total variance. Now let us put the values in the formula. Then we need to look at the tables of mean and SD to find out the probability. There are two different types of tables. One-tailed and two-tailed for the standard normal curve. In one-tailed table, the tabulated value corresponding to the calculated value 1.51 is 0.4345. So, the probability is 0.5 plus 0.4345 is equal to 0.9345, means there are 93.45% chance that the project will be completed in 41 days. In two-tailed table, the tabulated value corresponding to the calculated value 1.51 is 0.9345. So, the probability is 93.45% that the project will be completed in 41 days. Step 8. Monitor the progress of the project and if required update the CPM or PERT diagram as the project progresses. Remember that project management is dynamic, and changes are inevitable. Regularly updating the project schedule and associated diagrams ensures that the project team remains informed, and potential issues can be proactively addressed. This is all about CPM and PERT.